River discharge is the volume of water flowing through a river channel. However, over a given year, a river's discharge will vary greatly depending on changes in the levels of precipitation, temperature, evapotranspiration, and drainage basin characteristics. Any sudden increase in the amount of water travelling down a river will cause flooding. For example, in February 2022, heavy rainfall in the Great Dividing Range added more water to the streams and rivers of the Northern Rivers region, leading to widespread flooding in the towns on the floodplains and near the coastline. This discharge of a river can be displayed on a graph called a flood hydrograph. This graph displays the amount of rainfall as a bar graph, and then the discharge of the river as a line graph. Flood hydrographs are useful in predicting how a river will behave during a time of intense rainfall. Flood hydrographs are a useful tool for local authorities who oversee planning flood prevention. The starting and finishing level of the line graph shows the base flow of a river. The base flow is the portion of the stream flow that has not run off. As stormwater enters the drainage basin, the discharge rates increase. This is shown as a sharp rise on the line graph and is called a rising limb. The highest flow in the channel is known as the peak discharge. The subsequent steep decline on the hydrograph represents the fall in discharge back to base level and is known as the receding limb. Since most rainwater falls onto the land before making its way into rivers, there is a lag time between the time of peak rainfall and peak discharge. A flood hydrograph can be used to work out how quickly this occurs. Not all hydrographs look the same, and this is due to a range of both physical and human factors that affect drainage basins. A drainage basin is an area of land where all flowing surface water converges to a single point, such as a river mouth, or flows into another body of water. Hydrographs are affected by the amount of precipitation that falls in a drainage basin. Heavier storms result in more water entering the drainage basin, which results in a higher discharge. The type of precipitation is also a major factor. Rainfall enters rivers far more quickly than snow does, which takes some time to melt before entering the streams and rivers. Therefore, the lag time is likely to be greater if the precipitation is snow rather than rain. However, when there is a rapid melting of snow, as can happen at the end of winter, the peak discharge can be higher. Large drainage basins such as the Amazon or Congo River basins catch more precipitation than smaller drainage basins do. Therefore, they have a higher peak flow and longer lag times. The shape of a drainage basin also impacts on runoff and the rate of discharge. For example, a long and narrow drainage basin will have a longer lag time and lower peak discharge than a basin that has a more circular shape due to the longer distance that runoff must have to travel to the river. Likewise, drainage basins with steep sides have shorter lag times than shallow basins because water flows rapidly down steep slopes to the river. Further, drainage basins with many streams will drain faster than drainage basins with fewer streams and will therefore have a shorter lag time. If the land surfaces of a drainage basin are already saturated, no further infiltration of the rocks and soils will occur, thereby increasing the surface runoff. Thus, rainwater will enter the rivers faster, reducing lag times. This is because surface runoff is much faster than water that would have otherwise reached the river through the slower process of infiltration. Rock type is also a factor. Impermeable rock surfaces such as granite have higher rates of surface runoff due to the reduced infiltration and through flow. Therefore, the lag time is shorter and there is an increase in peak discharge. By contrast, more permeable rocks such as limestone will have slower rates of runoff and higher rates of infiltration and through flow. Drainage basins with significant amounts of vegetation have a significant impact on hydrographs. Vegetation intercepts precipitation and slows the movement of water into river channels. This increases the lag time. Evapotranspiration of water in rainforests also causes the loss of water and thereby reduces the peak discharge of a river. Human-made drainage basins have a much shorter lag time and higher peak discharges than natural drainage basins, due to the impermeable nature of concrete and asphalt surfaces. For this reason, highly urbanized drainage basins are a high flood risk.